thank you for the introduction, Antonio, and also, of course, thank you to Fernando for the kind invitation to come. For me, it's a pleasure and an honor to give a talk here. And I'm going to explain some results which are contained in the last paper that that means Bill Mix and Antonio Ross and myself, have uploaded to archive some months ago. These results in that paper were announced a long time ago, more than 10 years ago. The reason why we uploaded the paper some months ago is just because they were based, the original argument that even I don't remember, so don't ask me, please, was based on certain results in Condé-Minicossi theory that never appeared in final form. Okay? So this made us to try to develop the understanding of how to take limits on sequences of embedded minimal surfaces in Euclidean 3 space to certain kind of singular minimal laminations. Okay? And once we more or less sort of understood how to take such limits, then we finally uploaded this paper, and also 1 year ago, more or less, another one which is on the partial result on the Hoffman mixed conjecture that says that the number of ends of embedded minimal surface in R3 of finite total curvature cannot be bigger than the genus plus 2. This is what the conjecture says, right? And what we showed by using more or less arguments which are related to the ones so I'm going to explain today is that there exists a constant depending only on the genus for the number of ends. I mean, you cannot have more than a certain number of ends only depending on the genus, but the constant is not explicit. Okay? So today I'm going to talk about the embedded Calabi-Yau problem. So let me go directly to posing the problem. All surfaces will be orientable for me. And Calabi, the year I was born, posed a question if it's possible to immerse a minimal surface in a complete way inside, say, a ball or half space. Okay? It happens, well, Xavier proved that you can do it in a slab, actually, and Nadirashvili, in a very famous result, showed that the existence of a complete immersed minimal disk in a ball, right? And then Yau came and added a word, the word embedded, which is there in red, no? Right? In 2000 to the question, and the question in this setting remains open so far. Okay? And I want to mention a result which is very important in the classical theory of minimal surfaces, that is the half-space theorem by Hoffman and Mix, that says that you cannot even immerse a surface in a half space if the surface is proper. So proper and complete, I mean, there is a relationship between them in R3, which is proper, of course, implies complete. And it's natural to think under which conditions, by looking at these results, complete implies proper. And that's the embedded Calabi-Yau problem. I'm going to restrict only to embedded surfaces, right? Because for immersed, it's not true. Okay? Okay, so I'm going to show you now 3 results that you can barely see that imply properness and the completeness for embedded minimal surfaces, assuming some additional assumption. The first one, proven by Bill, Antonio, and myself some years ago, we assume finite genus and also locally bounded Gaussian curvature. That's the meaning of Km, right? Which is exactly the same as saying that the surface can be viewed as a leaf in a minimal lamination. Then it has to be proper. More important for our talk will be this result. Condé-Minicossi showed in 2008, or published in 2008, that a complete, that's the meaning of CEMS, complete embedded minimal surface, in R3 of finite topology, so finite genus and finitely many ends, is proper. Okay? And based on this, the arguments in this proof, Bill and Harold Rosenberg showed published in Duke 2006 that if you add positive injectivity radius as a hypothesis, then complete also implies proper. Okay? Then what I'm going to show that we can generalize here from finite topology to finite genus. adding something else that I will try to justify next. Okay? So I start with my favorite complete, or your favorite complete embedded minimal surface in R3, which has, of course, to be non-compact. So you have ways to go to infinity. This is the set of ends. Okay? It's not empty, the set of ends. Here you have the rigorous definition. I'm not going to bother you with the definition, but I presume that everybody knows the definition, right? What is more important for me is what is the meaning for a non-compact subdomain in a surface with compact boundary to represent an end. Represent an end means that whenever you take, well, an end rigorously is a equivalence relation of proper arcs. What it means is that every proper arc, it doesn't matter which representative you take in the class, will be eventually contained in that non-compact subdomain, right? So that's a definition. And then if we want, don't forget that we want to know some conditions in order to imply properness, okay? To be able to get properness. So if the surface were proper in the end, it would have countably many ends. This is a result, a consequence of a result by Kolen-Kuznets and Rosenberg. And what we are going to show is that if you put that hypothesis, so finite genus plus countably many ends, then you can prove properness. Okay? So that's the main theorem. Although I'm going to show you the completely a generalization of that, which is what we actually prove in the paper, right? But in order to do that, I need another definition. So I need to say distinguish between two types of ends. It turns out that the set of ends of in my setting can be endowed with a natural topology. And with the topology, you can embed that topological space into 0, 1 with the interval 0, 1 with its usual topology. So then an end is said to be simple if it is isolated, and a limit end if it is not isolated. In order to think about this, I would tell you that think of the Riemann minimal example. This is a picture, very nice, of the Riemann minimal example, because it's topological. It's not minimal, of course, but you have there a cylinder, right? And at every height in space, you have to imagine a minimal surface. At every height in space, and heights are represented by heights in this picture, you see a circle of varying radius continuously. So when you pass through a flat end, then what you see is a straight line, right? And then topologically, this is a completely perfect picture for a Riemann minimal example. But I can think of my cylinder as this, twice functional sphere, and then the flat ends, the planar ends, are just one sequence that goes limits to north and south pole. Then these are the two limit ends in this case, and the other ends are simple, right? All the flat ends of the Riemann minimal examples are simple. Okay, with this in mind, this is the completely general, say, situation in which we can prove the theorem.
For the limit end, is there a representative like the last slide?
Well, a representative of this end is here, a neighborhood that has infinitely many flat ends inside. You see? Okay. And only one limit end, say. Okay, so if you have a complete embedded minimal surface in R3 with compact boundary, finite genus, infinitely many ends, then if the surface has countably many limit ends, not necessarily ends, but limit ends, countably many, then it's proper, and in the end it only has one or two limit ends. I have to say that in that setting of finite genus, we knew some years ago that it's impossible to have one limit end only if you have empty boundary. Okay, so the one limit end case only happens with boundary, like in half of the Riemann minimal example. Cut here, chop off here, right? And you see a representative of the end. This is what Otis was thinking about. Okay, so now in one slide I can give you a sketch of the proof, but you have to trust me, of course. I will not say everything. You have to. And then we will devote the remaining part of the talk to explain more or less what I'm going to assume. So I'm going to take a surface, like in the statement of the theorem, and then I'm going to focus on not on the set of ends, but on the set of limit ends, which by hypothesis is countable. But this is a metric space with the topology I told you before, right? And countable, and you can apply, and it's complete, so you can apply Ber's theorem, and then it says that the set of isolated points in that set will be dense, okay? But what is the set, or what is an isolated point in the set of limit ends? Well, it's nothing but a limit end, which is a limit of simple ends, but it's not a limit of limit ends, right? Say it again? No. Okay. So right? No, so those kinds, so the simple possible limit end you can think of, that is a isolated point. Well, the set of those is isolated, is dense, sorry, is dense. So then assume these two lines here, and then of course we will prove the theorem. If M has only one or two simple limit end, is proper, right? Well, of course, no? It is exactly what I want to conclude. And second is that M cannot have three simple limit ends. If M does not have three simple limit ends by density of the set of simple limit ends, it cannot have more than three limit ends. Cannot have three or more limit ends. Doesn't matter if they are simple limit ends or not. Okay? And there you are in this situation, and then it's proper. Okay? So we had to prove these two lines, and everything reduces to that. And everything is going to be implied by the, well, this is, forget about this thing. This is what I said before. If you don't have boundary, it cannot have one limit end. It has to have two. Okay? So, but, okay. So the two lines are going to be implied by what I call the Christmas tree picture, or we call. The Christmas tree picture is, well, it's a statement that I have divided here in two parts. This line implies 1, and the remaining part will imply 2. So let me explain why. It says if you take a simple limit end, right, of M, and you assume genus 0, and genus 0 can be assumed for free because since the M and the surface M has finite genus, then you can leave all the genus in the compact part of the surface, so you can take a representative of this kind with genus 0, okay? That is proper. Why this implies that the whole surface is proper, assuming the hypothesis here? Because, well, you have either one or two simple limit ends, each of which is proper by this line here, okay? And then what happens with the remaining part of the surface? Well, the remaining part has finite topology, because if it had infinitely many ends, it would have another limit end, okay? But you only have one or two. So what you have done is to, say, split the surface into three, possibly two, but three in general, domains. Two simple limit ends, which are proper, and a finite topology subdomain with compact boundary. Okay, the boundary is shared by the three pieces, right? Two by two. And each of which is proper because the third finite topology part is proper by Coldi-Minicozzi, has finite topology. Okay, so the surface has to be proper. So this part implies 1, and the second part implies 2. And let me explain what is the meaning of that. You can take a representative of the end, and after a translation, rotation, and homotherapy in R3, all the simple ends will have finite total curvature. I would like you to think about the Riemann minimal example, right? But well, all will have finite total curvature in the Riemann minimal examples. They are planar. All with non-positive logarithmic growth, they are 0. The limit then is the top end, so I'm thinking about the top half of a minimal example. The boundary is a planar curve in the plane x3 equals 0 that bounds a convex disk, or a round disk in the case of Riemann, so that the interior of that disk does not intersect this E again. And finally, the topology of E is exactly the same of our one half of a Riemann minimal example, which is the meaning of R plus. Okay? In one picture, I can show you what the theorem, what the proposition, the second part says. Is that you can find a representative as nice as this picture. Okay? So here you have the boundary that encloses a convex disk. All these ends have finite curvature. Maybe they are planar, or they are catenoidal with negative logarithmic growth, and the simple limit is the top end, right? Okay, so now I want to show you why this second part implies 2, which finishes the theorem. And then I will try to explain some of the arguments that imply properness. Okay. Okay. So assume by contradiction that we have at least 3 simple limit ends. Apply the Christmas tree picture to each of the 3. Okay? Then, because of embeddedness of the whole surface, you can have one where the simple end is the top end, the other one would be the bottom end, but then you have a third one. So then you have 2 pointing in the same direction. So let us assume they are pointing, I mean, the limit end is the top end in 2 of them, no? That I'm going to call E1 and E2. And here you have 2 instances of the Christmas tree picture. Okay? So E1 has its boundary here, height 0, and maybe E2 is higher. I don't know which one is higher. After relabeling, I can think of this situation. And because I said in the interior of that disk, E1 doesn't enter again, right? Then what happens is that if you glue this DE2 flat disk there to E2, and now you consider the part of E1 which enters there, then you can define, I don't know if you see it clearly, but you can define in gray in the picture a 3-manifold whose boundary is a collection of minimal surfaces, and the angles at the boundary are correct in the sense that you can solve plateau problems there. Okay? What I want you to do is to solve the plateau problem with this boundary, the boundary of E2. And this way you can produce a surface which will be area minimizing, and then by Fischer-Kolbry finite curvature, which means in particular that it has finitely many ends, all of finite curvature, so it have a highest end with which is catenoidal with positive logarithmic growth, and then you can finish in a lot of ways you can find a contradiction. No? For instance, because it's constrained to be in between ends of the former description of the Christmas tree with non-positive logarithmic growth. This is one possibility, or you can do what is written here about. Anyway, you can finish. Okay, so now what? Right. So I have more or less 40 minutes to try to convince you that properness holds for the Christmas tree picture, and this is my goal. Okay. So take now and forever a simple limit end E representative that I can assume has genus 0, as I explained before, of a complete embedded minimal surface, and I want to prove proper for E. Well, the description, topological description of my end is like here, more or less, but I don't know how this embeds in space, right? So the topological picture is just the unit disk. This is the limit end, and now you have here a sequence going to of simple ends going to there, right? That I can, for instance, parameter this way. Crucial for us in the argument will be the minimal lamination closure theorem. That's the meaning of this, by Mix and Rosenberg. That says, in this setting with compact boundary, that if the injectivity radius function of a complete embedded minimal surface with a compact boundary, think of this M will be my E. is positive, bigger than some epsilon, bigger than 0, outside some neighborhood of the boundary, then the surface is proper. Okay? So that's the only thing we had to prove in our setting. Yes, so this is this line. And also, this is called the Minkowski. Well, no, yes, it is called. If it has finite topology, they proved by Bill and Harold that actually the injectivity radius is bigger than some epsilon bigger than 0 outside of some delta neighborhood of the boundary. Okay, so in particular, it's proper. Okay, so now I want to describe my next step. I want to describe the geometry in a space of all these ends, the simple ones. Okay, no, this one. This is the most difficult, the simple ones. So what I'm going to do is, well, I'm going to chop off my surface here. I'm going to consider a circle here, topologically. And then En, it's going to be from here to there in the surface, right? And I think of this embedded in R3, minimally. Then that thing has compact boundary and finally many ends. So by Kolde-Minkowski, it will be proper. And since it is proper by Kolen, it has these ends are catenoidal or planar. That by embeddedness, I can rotate the surface so that they're graphical over their projection on the horizontal plane. Okay? And I can do this for any n. Of course, because of embeddedness of the whole surface, I don't lose the, say, verticality or the direction. So it's the same forever. Okay? Good. Now we are going to argue by contradiction. Remember that I want to show that the injectivity radius is bigger than some epsilon, bigger than 0 outside of some neighborhood of the boundary. So suppose not. That means that you can find a sequence of points in E such that they are far from the boundary, delta far at least, but the injectivity radius function goes to 0 there. And then what you have is little necks forming in the surface. Then we have a say machinery called rescaling by topology that says that you can change the Qn points by other points Pn with the same property of having injectivity radius going to 0, but being even worse than the Qn in the sense that the injectivity radius goes to 0 more quickly in the more quickly. I mean, I will explain in a minute. That if okay, first they are close by the Qn points. Second, you can find a sequence of radii going to 0, so that if you think of the component, the closure of the component of the surface intersect the point P, the ball center at Pn of radius epsilon n that contain Pn's, it happens that that component is compact with boundary and the boundary of the ball. Okay? And this is the most important thing, which is that by rescaling by the inverse of the injectivity radius at the center, at Pn, then the rescaling surface that I'm going to call lambda n mn, or lambda m mn minus Pn in order to put Pn at the origin, the same, okay, turns out to have injectivity radius this thing here. So in particular is approximately 1. Okay? It's bigger than 1 minus 1 over n. Not only that, this, which is the radius of epsilon n in a scale, in the new scale, when you multiply by lambda n, goes to infinity, which means that this ball here will rescale to a bigger and bigger ball. And then you see more or less the Kolde-Minkowski picture forming, right? Then the sequence of rescaled MNs, right, up to a subsequence converges to one of two possibilities, either to a minimal, properly embedded minimal surface in R3 passing through the origin, injectivity radius at least 1 everywhere, 0 at the origin, or a minimal parking garage structure with 2 columns, something strange that I will explain in 1 minute. Okay, so go here again. So we said properly embedded minimal surface in R3, but since it's constructed from E by rescaling, by blowing up, it cannot have more genus. It has to have genus 0. So, and those are classified. We classified those, well, we and a lot of people, they are catenoid Riemann minimal examples. Only you only have these ones. Of course, you could have the helicoid in general, I mean, in the general setting, but since this has injectivity radius 1, it's not simply connected at the origin, right? It's not simply connected. So you rule out the helicoid, and then you end up with these two possibilities. What is a minimal parking garage structure? Well, it's just a foliation of R3 biplanes, that's all. But there is a nice structure happening there. In order to understand that structure, I want you to think about, again, Riemann minimal examples. Okay? Riemann minimal examples come in a one-parameter family. They are properly embedded, minimal surfaces, invariant by a translation, genus 0, infinitely many flat ends that I'm going to consider as horizontal, right? But they come in a one-parameter family. You can think of the family as, for instance, the flux or the period, if you want. I don't care. No, it's not the same, but for instance, the flux. The flux goes from horizontal to vertical. We are taking the two possibilities. It's an open, right? The limit in the vertical case for the flux is just the catenoid. I'm not interested in that now. The limit when the flux goes to horizontal is 2 helicoids. In order you to understand that, I want to think of the 3 pictures above. Are exactly the same surface. It's only 3 views of the same surface. The surface in red is one minimal example. And you see here there is a gray plane, no, plane of symmetry intersecting the surface. You see, then when the flux vector goes to horizontal, you start forming inside these 2 cylinders, which are not containing the surface, of course. You start seeing here a picture of the helicoid, you see? And by symmetry, this is rotating in one way, and this is rotating in the other way. They are oppositely rotating. So it's more or less this picture here. What happens is that if you take a scale so that not only the flux goes to horizontal, but also you keep this distance between the 2 cylinders fixed, then the convergence is to a foliation by horizontal planes of the red Riemann minimal examples. Okay? And something funny happens, which is that, of course, you see curvature blowing up along the axis of the forming helicoids. You see? So these are the 2 axes of the forming helicoids, and here in between you will have this symmetry plane. And what happens then is that the convergence is smooth outside from the singular set of convergence, which is just the collection of these 2 lines. Okay? Well, a limiting parking garage structure with 2 columns is exactly this, but instead of having it's a limit of Riemann minimal examples, it's a limit of a sequence, but with the same behavior in the limit. For later, I want you to know what is a connection loop. A connection loop is something that you can always take in a limiting parking garage forming, which is just before going to the limit. Okay? When the surface is the surface in the sequence is very degenerate, then you can go from a vicinity of one of the, say, axes to another one just by going in one, say, I don't know, horizontal layer, right? And then going up one layer, going down, going back to the original axis and then closing. You can do this always, right? And if you compute the flux along this closed curve, along the surface, in the Riemann minimal example, they will converge to a horizontal vector, as I said before, which is just this segment, the horizontal segment joining the 2 lines. But since you have to cover it twice, then you convert to double the length is double. Okay? Okay, so let us discard a Riemann minimal example in the limits. So we have to discard a Riemann minimal example, a limiting parking garage, and a catenoid, right? Riemann minimal example is the easiest one, so I'm going to start with this. So first thing is we will show that the limiting surface, M infinity, has vertical flux, which immediately implies that the planar ends in M infinity are tilted. right? Because a real minimal example cannot have vertical flux. Okay? So why the limit surface has vertical flux? Well, it has been obtained as a limit by blowing up. So what I'm going to do is that I'm going to take a wave circle, say a circle on the real minimal example, right? I don't know what is the situation of that circle in space, but this is a limit, because it's compact, it's a limit of closed curves in Mn up to the scaling, right? And what I'm going to do is proving that the flux of the real surface along gamma n is vertical, and I don't care if I'm changing the scale, because verticality is preserved. Okay? So I'm going to prove that this is vertical. Well, in order to do that, I'm going to discuss two possibilities. Either this is my boundary and this is the limit n. Either my curve is like that, this is gamma n, and encloses some finally many number of simple n's there. And then it's very easy, because in that case, gamma n is homologous to a finite collection of simple loops around the ends which have vertical flux, because the ends are, say, canonical, right? So in this case, it's trivial. And the other case, when well, up to passing to a subsequence, I can assume that it's always this, right? It's topologically concentric. So gamma n, and say here, for instance, gamma n plus k, right? And so on. And here in between, I have finitely many n's. Well, in that case, what I'm going to do is to, again, apply divergence theorem, and then I will know that the flux along gamma n is the same as the flux along gamma n plus k, plus the flux along all the ends that you trap in the annulus in between. But this is a vertical vector. So if you take horizontal components here, you have that the horizontal component of this is equal to the horizontal component of that, right? Which is the meaning of that. But the horizontal component of the flux in length is less than or equal to the length of the flux, which is less than or equal to the length of the curve, right? Because you are integrating the union conormal vector. But since you are doing a blow up, then the length of the gamma n goes to 0, which means that this thing has to be independent of anything, because it doesn't depend on anything, but it goes to 0, so it has to be 0. Okay? Which means that this is vertical. So now we know that the limit Riemann minimal example has tilted ends, and this is what I want you to keep in mind now. Okay? Okay, next step is a bit more complicated, so I'm going to wave hands more. Here is that I can find this picture below is part of E, the original surface, versus this part here, which is the limit Riemann minimal example. So there is a change of scale here by blowing up. Okay? So I claim that I can find a non-compact subdomain as the blue one that you see here in this picture, which means that it traps finitely many simple ends of E. It is bounded by its boundaries two almost circles that converge to, these are two real circles up to rescaling, right? And you see here the blue color is because this is in blue. So what happens, the meaning of this rectangle is that up to rescaling, you have conversions on compact subsets, only on compact subsets, right? The reason why I have used here 3 colors is in order to ensure that this delta n exists, you have to essentially avoid the boundary, original boundary of E. This say spends 1 color, and also the limit n spends a 2nd color. But since I can take infinitely many colors and put there in my Riemann example, I can find such a domain there. Now I'm going to use the domain, and well, I had to glue some disk and do something more technical there, but I'm going to essentially to use the domain as a barrier to define a 3-dimensional manifold with boundary to solve a plateau problem in it. How? Well, I'm going to I'm going to think of this orange curve here, which is supposed to represent a curve that winds once around one of the ends of this omega 1, 2, right? And since it's compact, it will be a limit of similar curves, although there is a change of scale there, of course. These are tiny. But okay? And I'm going to use this as a boundary for solving a plateau problem at one side of this blue delta n. And then I can create this surface Sn, which will be minimized, properly embedded, blah, blah, blah. And then because it has compact boundary, will be stable. We'll have a finite total curvature. So the ends are canonical again, right? And they are constrained to be, say, in between the ends of a delta n. In particular, since the simple ends of delta n are horizontal, the ends of the orange surface are horizontal as well. But the point is that, and now is when I'm going to wiggle, wave my hands, is that because it's constrained to be in between on compact parts of this picture, in between these two, and this is tilted, you find a contradiction. I mean, you have, on one hand, this scale has to be horizontal, on the other hand, has to be tilted. It's impossible. Okay? So that is more or less the idea.
Does that use something like a flux? How do you transmit the information from infinity to the compact? Like, how do you transmit that information?
Well, essentially, it's because you can, well, this has finite index, right? So if you go sufficiently far, it will be stable. And then it cannot bend a lot. Okay, the Gauss map cannot be too large, say. So you cannot move the direction. This direction here, which is horizontal, cannot be moved, essentially. Of course, you had to do something else. Right. So that shows that that the Riemann-Minimal example is discarded. Now, how do you discard a limiting parking garage? Well, because a limiting parking garage has the geometry, let me say that, of a very generated Riemann-Minimal example. So I'm going to see if I can reproduce the argument again. The main part of this argument was that the ends here are tilted. Now, the fact that the ends are tilted came from the fact that the flux is vertical. Now, if you take a connection loop on my limiting parking garage, compact, of course, then compute the flux along this connection loop, right? And then again, the same argument that I showed you in that part of the blackboard shows that this flux is vertical. But the flux of a limiting parking garage goes in the direction of the planes of the foliation, which means that the planes are in fact vertical. They are not only tilted, they are completely tilted at the vertical. So you can do the argument. I mean, in the end, you can reproduce the argument. Okay? So let's go to discarding the catenate. And this is by far the most difficult part. So assume that the limit surface now is the catenate after the first, because it's going to be a second, there's going to be a second blowing up. Blow up argument, and then I'm going to take my west circle of the limit catenoid. I'm going to reproduce this curve gamma n along the sequence. Then by the same arguments, the catenate is placed vertically in R3 because the flux has to be vertical. It's the same argument, so I don't lose time here. And then I'm going to think of three possibilities for the gamma n's, which are encoded in this picture, right? Up to subsequence, I can think of every gamma n is in one of these three possibilities. So always this, always that, always that. The first case is when gamma n encloses a finite topology domain in E, but at least with two ends. Important, at least two. The second case is when they are topologically concentric. And the third case, which seems to be the easiest one, it is not the easiest one. Okay? That case is when it encloses only one end. So this is like that, but here only one end, there 2, 3, whatever, but more than one. Okay, so the strategy will be the following. I have all of this because I have to put ways of escaping because of the time, right? So we are going to rule out D1 by application of the Lopez-Ross argument, the deformation Lopez-Ross deformation argument. We will also use a result by Bill and Brian White. In order to rule out D2, we will prove this lemma that surprisingly assumes that D3 holds. You will see why. Okay, but here what lemma 2 says is that if the points where you are doing the blowing up are converging in R3, which in principle you don't know, they could escape in space, but if they converge and D3 holds, then the whole end lies at one side of a plane, horizontal plane passing through this point. So in particular, it's contained in a half space. Okay? With that lemma, we will rule out D2. But in order to do that, we will rescale again by topology and apply 2 other theorems that I will tell you. And the most difficult part is discarding D3, because then we will have to rescale by topology again, apply the minimal lamination closure theorem, and apply the one-sided curvature estimate by Calabi-Yau. Okay? But let's go little by little. So let us rule out D1. So suppose that C1 holds, which means the limit is a catenoid, and D1 holds, which means that every gamma n encloses at least 2 ends. That means that, well, I don't have pictures as nice as Christina's, but I have pictures. This one, this thing, okay? That means the following. You have at least 2 ends enclosed in the abstract surface, I mean the abstract topological surface. Gamma n encloses at least 2 ends, okay? Which means that, me draw here, this is my, again, limit n, boundary of E, here is gamma n, and this is you have here at least 2 finitely many ends, and I'm going to call this domain here Rn, right? It's a domain, non-compact, compact boundary, finitely many ends, at least 2 in E. And it has vertical flux. Don't forget about this. It has vertical flux. Okay? So what I'm going to do, I'm going to choose because the limit is a catenoid, I can choose this Cn, which is a almost perfectly formed unstable piece of a catenoid. There, you see, in blue, in red. And because the ends of Rn are pointing down in this picture, okay, and you have at least 2, you have this at least 2 annular ends here. Okay. So now let me say something. If I don't know, but if Rn doesn't enter in this region, this shaded region, then if I glue the planar disk here bounded by gamma n to my Rn, right, I will separate R3. And in that setting, it's impossible to have vertical flux and at least 2 ends. You have to have only 1 end. This is something that Antonio proved a long time ago. Okay? So what I want to know is if Rn starts here, right, and goes down. I don't know later what it does, but eventually it could come up here and appear again here again. You see, something like that. But since Rn has finite topology and compact boundary, it is proper. Rn is proper. So if it comes inside, it has to go out again, because this is a compact region. Here, this is a flat disk, this is a flat disk. Okay? So it has to go out. And then I can think of this part here as a barrier to solving a plateau problem inside in the shaded region with this boundary and this boundary. This way, you will create another surface here. You see? Which will be stable because you minimize, right? You solve a plateau problem. But that is a contradiction because since this is a convex curve in a horizontal plane, and this is also a convex curve, then Brian White and Bill Meeks proved a long time ago that they only bound one stable annulus, right? And of course, here is my almost catenoid, which is unstable. The stable annulus is outside. So that thing cannot be inside, which means that Rn cannot enter, which means that you rule out this case, okay? Okay, so now we have ruled out this case. Let me show why lemma holds, and then I will try to convince you that I can rule out D2. Or maybe, I don't know, I will not have time to rule out D3, but. Okay, let me show this lemma. So again, if the points where the blowing up process is done, go to or converge to some finite points in R3, and for each n D3 holds, then the whole surface E lies at one side of that horizontal plane passing through the P infinity.
When you say D3 holds, you mean it doesn't occur?
D3 holds means that for every n, gamma n encloses just one end.
And so you're assuming that doesn't happen?
That happens.
Oh, okay.
That happens. It's not it doesn't happen. Happens. Okay? Trust me. Trust me. Okay, because it happens, then you have this proper annulus bounded by gamma n inside E, right, for every n. And then you have this picture, right? Now you see here gamma n, and underneath gamma n starts one region, well, non-compact subdomain inside E, which is Rn. Here I have written graphical. Well, if I move slightly this gamma n here in this direction, and I change this gamma n by this other gamma n, then it will be graphical, right? Because it's just one n which is enclosed here. Okay, so in particular, you have curvature estimates for this. You have curvature estimates here, but this part of this gamma n is shrinking to a point. And that's the hypothesis. Then, because you have curvature estimates, these graphs here, Rn, converge smoothly outside from this point in R3 to that plane minus this point. Okay? Now, why E has to lie at one side? Because if not, you will have this orange picture here. You will be able to find a point of transversal intersection between the plane, even between the plane minus the point, and E. And because of the convergence, the smooth convergence, then you are going to also I should use blue here, to intersect one of the RKs for K large enough in the sequence. But that means that you have found a non-embedded point in E, right? Which is impossible. Okay? So that means that this lemma holds, and now I'm going to show you how to use the lemma. So forget everything here. All right. Now we are coming back to our D2 situation. Remember, D2 means gamma n is topologically concentric with gamma n plus k, etc. Now, by playing more or less the same role, I said here that moving slightly gamma n in certain, changing gamma n in its homotopy class, you can think of gamma n as instead of the neck of a forming catenoid, as a neck where the catenoid has the boundary. The compact part of the catenoid has one of the circles, almost circles in its boundary, gamma n, like in here, you see. And then for k large, you have another gamma n plus k of the same sort. And you see another catenoid here, you see? And again, gamma n plus k is one of the curves in the boundary. And the region in between, I'm going to call it, before was Rn, now is Rnk. Okay? And in between, you have, by the convex hull property, you have at least one annular end. Okay? But finally, many. Now, it comes the question of what is the relative position between this picture and this picture? Is this picture inside? Is this picture inside that? I don't know. Well, they cannot intersect because they are parts of an embedded surface. Even I'm going to think about, I want you to think about say the topological ball bounded by this disk, flat disk, and the piece of catenate, right? So is this part inside? Well, you can show that eventually this part is inside that one. Why? Because otherwise, because Rnk is proper, again by finite topology and called Minicozzi, you can do again the same argument based on Bill and Brian Welch, okay? And do the same contradiction, which means that the only possibility is that this, which is much, much smaller than that one, because it is happening in a process where you are blowing up, and this is everything in the original scale. What you have exactly is this. I mean, of course, this second catenate is much smaller, but you wouldn't see it. Okay? So this is what happens. Maybe in between you will have ends, and you will have connections between. Okay, so, and this happens forever. I mean, in a sequence, this is what I say. Which means that you have a more smaller catenoids there, and then, well, after relabeling, I can think of Wn plus 1. Wn plus is just everything here. I mean, the topological ball, solid ball, enclosed by the two flat disks and the piece of a catenate, right? So the intersection of the balls, topological balls, is just a point that I call C infinity, which more or less is here. I don't know, but it's inside. It's topologically concentric. Everything is topologically concentric. And I claim that now I want you to think about the following. Every piece of E, the original surface, inside the big solid region, the big solid, say, catenate. Okay? So that is the interior of W1. Remove the point that you have created this way, and what I say is that everything in E in that set has locally positive injectivity radius. Why is that? And this is a subtle point. Why is that? Because if not, I'm going to do the same argument that I did before. I'm going to rescale by topology again. Okay, I can if I assume that the injectivity radius goes to 0. And then I will find again D1, D2, D3. But because of we have already ruled out D1, we can again rule out D1. D3 now can be ruled out now. Why? Because if D3 holds, because I'm assuming that this doesn't have positive injectivity radius, is because I see little necks forming in this compact region, so they can escape. And they will go to some point which is different from this one also. So that means that you have a point like this, I don't know, like here, where you see D3 forming. And then the lemma says that the complete end is at one side of this horizontal plane. That's impossible, because you see parts of the big catenoid, this one, which are above, and other part which is below. So D3 is also discarded. And finally, how do you discard D2? Because if D2 happens, then you will find catenaids, tiny catenaids, again the same situation, concentric, but converging to some point which is not C infinity, which is impossible because I have said that the catenaids form in a concentric way. So that means that E, that thing that you see there, has locally positive injectivity radius. Okay? 5 minutes. Good. Then, using the minimal lamination closure theorem, if you take the closure of that in the interior of W minus C infinity, that is a minimal lamination by the minimal lamination closure theorem. Okay? And of course, there is a leaf of this lamination that limits to C infinity. And then, I'm not going to explain why, but there is no limit leaf of this lamination L passing through C infinity. So in particular, what I say is that there is a neighborhood, very small neighborhood of C infinity called U, so that the intersection is proper, of the lamination with U is proper. But again, since E has genus 0, then you have here an intersection that is possibly non-connected. But is a surface of genus 0, which is properly embedded in R3, in the puncture ball. Okay, U minus the C infinity. Okay, and then in a previous paper, Bill, Antonio, and myself, we proved in local removable singularity theorem, because of finite genus, you can extend across this lamination, which is a contradiction. It's impossible to extend across if it's a limit of tiny catenaries. This way, you rule out D2. Okay, and I have 5 minutes, so I'm completely sure I will not be able to rule out D3. Yeah, so I think it's better to stop here. Okay, thank you for your attention.